Every mystery in the universe begins with a quiet question, and tonight's begins at the edge of something unimaginably dark. A place where light bends like soft ribbon, where time stretches into long, slow breaths, and where the universe holds its secrets behind a veil of silent gravity. The black hole information paradox is one of those secrets, a whisper in physics that refuses to fade. Welcome to AstraFlow. Here, science drifts like starlight, and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing find its rhythm, and your mind float through wonder. Before we begin, I'd love to know where you're listening from. Are you lying in bed under city lights, or watching the stars from somewhere quiet? Tell me in the comments. It's always peaceful to imagine the AstraFlow community scattered across the world, drifting together through the same sky. And if this calm journey brings you peace, you can gently support AstraFlow by liking this video or subscribing. It helps this little corner of the cosmos keep glowing. Now, let's begin tonight's voyage into the quiet story of the black hole information paradox, a puzzle that sits at the meeting point of gravity, quantum theory, and the soft patience of time. Imagine yourself drifting toward a black hole, not in fear, but as if you were floating toward a dark horizon of thought. Space curves smoothly around you. Light stretches into long red waves that ripple like slow-moving embers. Time itself begins to thicken. Seconds elongate until they feel like minutes, then hours. There is no sound here, only the deep hum of your own breath echoing through the stillness. This horizon, the event horizon, is the silent threshold where the paradox begins. For decades, physicists believed that anything crossing this boundary was gone forever, its information erased from the universe. But nature has a rule. Information like memory should never truly vanish. It might change shape, it might hide, but it should not be destroyed. And so, the paradox emerges like a soft contradiction. Black holes erase information. The universe says they cannot. And somewhere between these two claims lies a mystery so gentle and yet so deep that it has guided generations of thinkers into long nights of contemplation. Nights perhaps not so different from this one. Tonight we will drift through that mystery together, letting it unfold like a slow tide in the dark. There is no rush. There is only curiosity flowing quietly through the cosmos. What does it mean for something to disappear? Not in the simple sense of slipping out of sight, but in the deeper, quieter way. The way a thought dissolves before you can catch it, or a dream fades the moment you wake. The universe, for all its vastness, rarely allows true disappearance. Stars collapse but leave ashes. Light travels until the end of time. Even the faintest particle carries a record of where it has been. And yet black holes challenge this gentle rule. They pose a question that refuses to fade. Can information truly be lost? As you lie there, perhaps easing into stillness, imagine this question drifting like a soft thread through the cosmos. It does not demand anything. It does not disturb your calm. It simply floats, patient and unhurried, inviting your mind to wander with it. The closer we look at black holes, the stranger the question becomes. Not sharp or alarming, but quietly profound, like a shadow stretching across a dim horizon. In daily life, we sense that events leave traces. A voice leaves an echo. A footprint presses into sand. Even when erased, some faint sign remains, waiting to be read by time. Physics believes the same, that every particle, every spin, every flicker of energy carries information, and that this information must always endure. It is one of the principles that holds the universe together like a long, unbroken story. But when something crosses the event horizon of a black hole, that story seems to be torn. The object vanishes from sight. Light itself cannot escape. From the outside, it appears as though everything that object ever was, its structure, its motion, its quantum details, dissolves into silence, and if the black hole eventually evaporates through Hawking radiation, shrinking until nothing remains, the universe is left with a puzzle. Where did the information go? This question does not shout. It does not shake the foundations of your rest. It simply lingers, like a single note held beneath the noise of the world, reminding us that even the darkest places carry meaning. Tonight we follow this question not to solve it quickly, but to let it open slowly, to let its edges soften, to let its mystery become an invitation to breathe deeper, to drift further, and to feel the quiet presence of the cosmos around you. The paradox begins here, with a gentle inquiry into memory, light, and gravity. And with the simple wonder of asking whether the universe ever forgets. Before we wander deeper, let's pause for a moment, just long enough to hold the entire paradox in a single, quiet breath. Black holes are simple in one way and impossibly complex in another. They are born from collapsing stars shaped by the gravity of their own weight and wrapped in a perfectly smooth horizon. They seem final, silent, absolute. And yet, within that calm exterior lies one of the most delicate contradictions physics has ever faced. Imagine the universe as a storyteller who never forgets any detail. Every particle that moves, every photon that glows, every atom that drifts through space leaves a record written into the fabric of reality. This is the principle of information conservation, the idea that the universe's memory is permanent. It may change shape, but it never vanishes. Now imagine a black hole as a quiet editor who removes entire pages from the book. Something falls in, a star, a particle, a breath of gas, even a beam of light. And from the outside, it looks as though the universe loses track of it entirely. The object's information is sealed behind the event horizon, hidden from the rest of space-time. According to classical physics, nothing escapes that boundary. No light, no message, no memory. Then Stephen Hawking added a new twist, a gentle whisper from quantum mechanics. Black holes, he discovered, are not perfectly silent. They glow, faintly, with Hawking radiation, slowly evaporating over unimaginable stretches of time. And if they evaporate completely, fading into nothing, then the information about what fell into them seems to fade as well. But nature says this cannot happen, and so the paradox rises. If the black hole disappears, and the information disappears with it, then the universe's most sacred rule is broken. But if the information somehow survives, where does it go? How does it escape a place that nothing can escape? This tension, quiet, persistent, unresolved, is what physicists call the black hole information paradox. It is not chaotic. It is not frightening. It is simply profound, like a soft chord that never quite resolves, echoing across time. As you listen, there is no need to hold the full weight of the paradox. Let it drift. Let it settle. Let the idea become a gentle presence in the background of your thoughts. Tonight's journey will unfold slowly, piece by piece, revealing how scientists have tried to reconcile gravity's deep silence with quantum theory's insistence on memory. For now, we only breathe with the paradox, one simple contradiction held between two truths the universe refuses to abandon. To understand the paradox, we first drift toward the black hole itself, not as a danger, but as a quiet monument carved by gravity. A black hole begins with a star many times heavier than our sun, a star that burns fiercely for millions of years before its fuel runs out. When that final moment arrives, the star cannot hold its own weight. Its core collapses inward, its outer layers explode outward, and what remains is a point of gravity so dense, so compact, that space curves sharply around it like fabric pulled tight, but the black hole is not truly a point. It is better imagined as a region, a dark sphere surrounded by an invisible boundary. This boundary is the event horizon, the place where escape becomes impossible. not because anything pushes you back, but because space-time curves so deeply that all paths, even the path of light, bend inward. From far away, the black hole looks oddly simple. It has no texture, no marks, no features, just a smooth horizon, quietly turning in the dark. According to classical physics, it can be fully described with only 3 numbers: its mass, its spin, and its electric charge. Everything else, every detail of what formed it, disappears from view. A star with 1,000,000 unique qualities collapses into an object with only 3. This striking simplicity, called the no-hair theorem, whispers the first clue to the paradox. If a black hole hides every detail about what created it, where does that information go? Is it erased? Is it encoded somewhere we cannot see? Or does it linger in some subtle way beyond our understanding? Imagine floating closer, letting the gravity pull gently at your thoughts. Space-time begins to stretch. Clocks near the horizon slow down. A beam of light, once bright, becomes redder and fainter, as if the universe itself is taking a long, deep exhale. To you, the horizon looks calm, smooth as ink, quiet as sleep. But beneath that surface lies a region where physics begins to argue with itself. As you drift there in your mind, nothing is rushed. The black hole is patient. It has existed for billions of years and will exist for billions more. It invites you to contemplate not its violence, but its serenity, the way it simplifies complexity, the way it curves reality, the way it holds so much mystery in such a small, dark form. Tonight, we meet the black hole not as a monster, but as a silent teacher. And our first lesson is this: what looks simple from afar may hide the deepest stories in the universe. As we drift closer in imagination, the black hole reveals its quiet threshold, the event horizon, the boundary beyond which no path leads back to the world we know. This horizon is not a wall, nor a surface you could ever touch. It is simply a place where space-time bends so deeply that every possible direction, even the one pointing outward, curves inward instead. Crossing it feels no different than floating through a patch of still air, yet it marks a point of no return in the mathematics of gravity. From far away, the event horizon seems frozen in time. Light approaching it stretches and slows, its colours sliding into red like embers fading at dusk. A falling object appears to pause at the edge, moving slower and slower until it becomes almost motionless to the distant observer. But this stillness is an illusion shaped by relativity, a gentle reminder that time flows differently in different places. Inside your mind's quiet space, picture the horizon as a soft, shimmering envelope. Nothing dramatic happens as you cross it. Physics doesn't scream. The universe doesn't tear. Instead, the rules continue smoothly, just guided by a stronger and stronger curvature of space-time. For the falling traveller, the crossing is seamless, but for the universe outside, everything past that point becomes unreachable. This disconnect is part of what makes black holes feel so mysterious. 2 truths exist at once. From the outside, nothing escapes the horizon. From the inside, crossing it feels perfectly ordinary. And at the centre, hidden far beyond what the horizon allows us to see, lies the singularity, a point where classical mathematics falters and our known laws of nature fall silent. The event horizon is the stage upon which the information paradox performs its quiet drama. Everything that falls in carries information. The pattern of particles, the quantum details, the structure of matter. But once it crosses that invisible line, the outside universe loses all access to those details. They seem trapped, sealed away in darkness. As you lie there listening, let this image settle into a soft calm. The horizon is not a violent edge, but a boundary defined by the flow of space-time, a place where paths curve inward like gentle spirals, where the universe's memory appears to dim. It is the silence of the horizon, its ability to hide information completely, that begins to stir the paradox we will explore. For now, simply rest with the idea that the universe has thresholds. Some we see, some we feel, some we can only imagine while drifting into the night. As we continue drifting deeper into tonight's quiet journey, imagine a single beam of light approaching a black hole. Light is usually our universe's great escape artist. Nothing moves faster, nothing slips through darkness more easily. Yet here, near the horizon, even light begins to struggle. Its path bends inward, drawn by the immense curvature of space-time, and its colour stretches into deeper and deeper shades of red. What was once bright and quick becomes slow and dim, like a lantern fading in a long hallway. From a distance, this transformation feels almost poetic. To an outside observer, the beam of light appears to hesitate at the edge, losing energy, fading into darkness. It never quite crosses the boundary in our view. Instead, it stretches thin, like a whispered word elongated across time. But through the eyes of the light itself, if such a thing were possible, the journey continues smoothly. It moves forward, unimpeded, crossing the event horizon without ever noticing the moment it became trapped. This dual perspective is one of the strange gifts of relativity. What appears frozen from afar flows effortlessly from within. Two realities coexist, each true in its own frame of reference, each describing the same moment yet telling a different story. And in that contrast lies a quiet beauty, a reminder that the universe is not limited to a single viewpoint or a single rhythm. As the light falls deeper into the gravitational well, its energy continues to drain away. Photons that once carried information in their wavelength, their precise colour, their subtle variations, lose that detail as they stretch. For the outside universe, the information seems to fade into irretrievable silence. Yet physics insists that information cannot simply vanish. Even as light dims, the patterns it carried must persist somewhere. Imagine lying back, your breathing soft, feeling the slow stretch of time near the horizon. The fate of falling light mirrors the fate of falling matter. Everything that crosses the boundary appears to lose its ability to communicate with the cosmos. The black hole becomes a keeper of secrets, holding what it consumes with perfect silence. And yet, it is this very silence that fuels the paradox. If the universe never destroys information, then the fading of light must be an illusion hiding some deeper truth. Perhaps the horizon stores it. Perhaps it transforms it. Perhaps the information waits in subtle vibrations we have not yet learned to hear. For now, we simply follow the path of falling light, a path that slows, stretches, and finally disappears from view, leaving the question of its ultimate fate to linger gently in the dark. Before we go any deeper into the heart of the paradox, we pause to understand something quiet but essential. What physicists mean when they talk about information. It's not memory in the emotional sense, nor knowledge written in books. In physics, information is simply the pattern of reality, the exact arrangement of particles, the way they spin, the way they move, the energies they carry, and the subtle quantum states that define them. Every object, every atom, every flicker of light contains a blueprint of itself woven into the fabric of the universe. Imagine placing a leaf in a river. Even if the leaf disappears downstream, the ripples it leaves behind tell a story. They record its shape, its weight, its motion. In that same way, information in physics describes the imprint an object leaves on the world, even after the object changes form. Burning a log turns wood into smoke, heat, and ash. But if we had perfect knowledge, we could in principle reconstruct everything from those remnants. The information is transformed, not lost. This belief runs deep in science. It is a promise the universe seems to keep, that reality unfolds in ways that are reversible in principle, even if not in practice. Quantum mechanics strengthens this promise further, insisting that every state evolves mathematically into another state with no missing pieces. The universe, at its most fundamental level, behaves like a perfect recorder, and this makes information sacred. If information could be destroyed, truly destroyed, the laws of physics would unravel, predictions would lose meaning, time would not flow cleanly from past to future. The universe's story would contain missing pages that no principle could recover. As you lie there listening, let this idea drift softly. Information is not weighty. It does not shout. It does not glow. It is simply the subtle structure behind everything, the quiet arrangement that makes a thing what it is. When physicists say information cannot be lost, they aren't speaking poetically. They mean that without this rule, the entire mathematical harmony of the cosmos would fall out of tune. Now, bring this idea to the edge of a black hole. When something falls in, the universe outside loses all access to its information. The structure, the patterns, the quantum details, they seem to vanish behind a veil no light can pierce. And if the black hole evaporates completely, taking those details with it, then the universe's unbreakable rule appears broken. This is why the information paradox matters. Not because of destruction, but because of broken harmony. It is a whisper telling us that either black holes do something we do not yet understand, or the very foundations of physics must be rewritten. Let that thought settle gently, like dust floating in a warm beam of moonlight. Now that we understand what information means in physics, the quiet blueprint woven into every particle, we can return to the black hole and watch what happens when these two ideas meet. Imagine a simple object drifting toward the event horizon, a pebble, a burst of light, a strand of gas, even a single atom. Each carries a unique pattern of information. Each holds quantum details that, according to the universe's rules, should never be erased. But when they fall into a black hole, something strange begins to unfold. To an outside observer, all the object's properties fade as it approaches the horizon. Its colours stretch into red, its motion slows, its signals weaken until they become impossible to detect. The information that once defined the object, its structure, its quantum state, becomes inaccessible, locked behind the boundary of no return. It is not simply hidden, it is unreachable by any means the universe seems to allow. Inside your imagination, picture this moment not as violent but as quiet. The object drifts through the horizon with no sudden shift, no jolt, no breaking of physical laws. Like stepping from one room into another, the crossing feels seamless. Yet from the outside, its story ends abruptly. The universe loses track of where the information went. This is the first layer of the paradox. Information becomes sealed away, not destroyed, but no longer visible to the world beyond. It is as if a chapter of the cosmic book has been tucked into a locked drawer. For many years, physicists accepted this idea reluctantly. Black holes swallow information, they thought, and the universe simply learns to live with that silence. But then came Hawking's quiet revelation. Black holes are not eternal. They emit a faint glow, Hawking radiation, which causes them to evaporate over time. They shrink little by little, until eventually they fade completely, and this deepens the puzzle. If the black hole disappears entirely, and the information inside never comes out, then the universe has lost something forever. The leaf's ripples have vanished, the log's ashes tell no full story, the cosmic rule of information conservation seems broken. As you lie there drifting, imagine the black hole as a dark library that burns down slowly, one atom at a time, while none of its books escape the fire. The universe is left with empty space where a mystery once was, yet physics insists the books cannot be destroyed. So where are they? Do they hide on the horizon? Do they leak out subtly in the radiation? Do they transform into something we have not yet learned to read? These questions are gentle steps deeper into the paradox. each leading us toward the next layer of mystery waiting in the dark. To move deeper into the paradox, we follow a discovery that began not with telescopes, but with quiet mathematics. In the 1970s, Stephen Hawking studied the strange meeting point between quantum mechanics and gravity, and from that meeting emerged a whisper, a prediction so soft and unexpected that it reshaped our understanding of black holes forever. He found that black holes are not perfectly dark. They glow faintly with a delicate emission now known as Hawking radiation. Imagine the space around a black hole not as empty but as a restless sea of quantum fluctuations. Particles and antiparticles appear in pairs, live for mere moments, and then vanish back into the vacuum. Normally, these short-lived pairs erase each other entirely, leaving the universe unchanged. But near the event horizon, the boundary between escape and no return, something subtle happens. One particle may fall inward, while the other escapes into space. The escaping particle becomes part of Hawking radiation, a soft, quiet glow the black hole sends into the universe. This glow is unimaginably gentle. If the sun were replaced with a black hole of equal mass, its Hawking radiation would be colder than the faintest whisper of cosmic background light. Yet over time, long silent ages, this radiation drains energy from the black hole. It shrinks, it cools, it fades. The giant becomes smaller, the smaller becomes tiny. Eventually, if left untouched, the black hole evaporates completely. As you breathe, slowly and softly, picture this process like a candle burning not with flame, but with darkness turning to light. A black hole, once born from the collapse of a star, gradually dissolves into the fabric of space. Nothing dramatic, no explosion, just a long, patient exhale from gravity itself. But this whisper of radiation carries a riddle. The particles that escape do not appear to contain the information the black hole swallowed. They are random, featureless, indistinguishable from ordinary heat. If a pebble, a star, or a breath of gas fell inside, the radiation gives no clue about what was lost. And so the paradox deepens. If the black hole evaporates entirely, where does the information go? Does it escape in the radiation? Does it cling to the horizon? Does it survive in some unfamiliar form? As you rest, allow this mystery to unfold without urgency. Hawking radiation is not a roar. It is a soft shimmer at the edge of gravity, a quiet hint that even the darkest places in the universe are not truly silent. It brings the black hole to life, and in time brings it to an end. And with that ending comes the paradox that has echoed for decades, a gentle contradiction between what gravity demands and what quantum mechanics refuses to allow. If you let your mind drift now toward deep cosmic time, you can imagine a black hole not as a permanent feature of the universe, but as something slowly changing, slowly fading, slowly giving its energy back to the space around it. A black hole may begin as a massive, fearsome remnant of a collapsed star, but through Hawking radiation, it begins a journey of quiet dissolution. Not in years, not in centuries, but over stretches of time so vast they make even galaxies seem young. Picture this. A black hole sits in an otherwise silent region of space. Nothing falls into it anymore. No stars wander too close. No gas drifts within reach. It is alone, glowing faintly with Hawking radiation, losing energy atom by atom. The glow is not bright. It is not warm. It is more like the softest breath a cosmic object could give, a constant, gentle release of particles into the darkness. Over trillions upon trillions of years, the black hole becomes smaller. Its event horizon shrinks, its curvature sharpens, and as it shrinks, the Hawking radiation becomes stronger, because smaller black holes radiate more intensely. What was once a near-eternal giant becomes a delicate ember of gravity, flickering quietly at the edge of existence. Eventually, in its final phase, the black hole reaches a size where quantum effects dominate completely. Its evaporation accelerates, though still far from violent in any human sense. And then, at last, it disappears. A long life ending not with a roar, but with a whisper, leaving behind only empty space where its dark presence once rested. But here lies the heart of the paradox. When the black hole vanishes, what happens to the information it once held? The particles released as Hawking radiation appear random, carrying no imprint of the things that fell inside. A star, a planet, a photon. All their details seem gone forever. Once the final glow fades, nothing remains. For physics, this is troubling. For the universe, it is impossible. Information, as we explored earlier, is meant to endure. Yet here, it appears erased, as if the cosmos has allowed a page of its history to be torn out and burned. As you lie there breathing softly, let this paradox settle like a smooth stone on still water. The vanishing of a black hole is not frightening. It is quiet, serene, inevitable. But the mystery it leaves behind ripples outward, touching everything we think we know about time, memory and the rules that guide reality. A giant fades, a question remains, and the universe whispers that answers must lie somewhere deeper still. Now, we stand at the quietest moment of the paradox, the moment after the black hole has vanished. Imagine the space it once occupied, a region once defined by immense gravity, now soft and empty, as gentle as any other corner of the cosmos. There is no trace of the event horizon, no remnant of the star that collapsed, no hint of the countless particles that may have fallen inward over billions of years. Everything is gone, dissolved into Hawking radiation that tells no story. This is where the puzzle deepens, because physics insists that every story must remain readable in principle. The universe keeps its ledger with perfect precision. Particles collide, transform, separate, recombine, but the information describing their states is always preserved. It may become impossible to decode, but it is never erased. Yet here, with the black hole evaporated completely, we face a soft contradiction. The information seems truly lost. Imagine a book thrown into a fire. The paper burns, the ink curls, the smoke rises, and yet, in theory, if you could track every molecule of ash, every wisp of vapour, every spark of heat, you could reconstruct the entire book. But if the black hole is the fire, Hawking radiation does not carry those traces. It is featureless, random. It does not whisper the faintest detail of the things it burns away. As you breathe gently, let this idea unfold like a slow wave. The paradox is not violent or chaotic. It is quiet, elegant, unsettling in a soft and thoughtful way. It tells us that our understanding of nature is incomplete, that somewhere between gravity and quantum mechanics lies a gap in the story, a missing connection in the universe's vast tapestry. This contradiction has stirred physicists for decades. Some propose that information does escape, encoded subtly in the Hawking radiation, too intricate for us to see. Others imagine that the event horizon stores information like a cosmic library, releasing it in ways we don't yet understand. Still others suggest that space-time itself may reshape the rules to protect the universe's memory. Whatever the answer, the paradox invites reflection. It reminds us that even in the calmest regions of thought, mysteries linger. It shows us that the universe is both familiar and strange, predictable and surprising, a place where the simplest assumptions can dissolve into uncertainty as gentle as falling dust. Tonight, we hold this puzzle lightly. The black hole is gone, but its questions remain, and those questions will guide our next steps, deeper into the heart of the mystery. To loosen the paradox gently, physicists began to rethink the very nature of the event horizon. Instead of seeing it as a simple boundary, a quiet line where escape becomes impossible, they imagined it as something far richer, a surface that does not merely separate inside from outside, but one that might store the information that falls through it. Like a cosmic screen, stretched across the darkness, holding patterns too subtle for ordinary perception. Imagine hovering near the event horizon, not with fear, but with curiosity softened by distance. The horizon looks smooth, perfectly dark, like ink poured across curved glass. Nothing written there is visible to the eye. Yet some physicists propose that every object falling inward leaves a kind of imprint on this surface, a faint record encoded in the horizon's microscopic structure. Not scratches or marks, but quantum patterns in the very geometry of space-time. This idea is known as the holographic principle, and it carries a beautiful, dreamlike suggestion. Everything inside the black hole may be represented on its surface, the way a three-dimensional scene can be projected onto a two-dimensional film. In this view, the horizon becomes a storyteller, holding the entire history of whatever has crossed it. The black hole's smoothness hides an unimaginable richness, as if the calm outer shell masks a library written in the language of quantum gravity. As you lie there in quiet thought, imagine information spreading out across the horizon like ripples of faint light. Each ripple is tiny, far smaller than atoms, yet together they might store every detail the universe refuses to forget. The interior of the black hole, then, becomes less mysterious, not because it is revealed, but because its secrets are carried outward to the boundary we can still observe. And if this holographic screen truly holds everything, then perhaps the information is never lost. When the black hole slowly evaporates through Hawking radiation, the information might be released bit by bit, woven subtly into the outgoing particles, not obviously, not brightly, but encoded in a way that only the universe itself could fully decipher. It is a gentle possibility, one that lets the black hole evaporate without erasing its past, one that allows gravity and quantum mechanics to keep their promises, one that transforms the event horizon from a simple edge into a guardian of memory. Whether this picture is complete, no one yet knows. But it has guided many thinkers to the idea that the horizon is not just a boundary, it is a canvas, a recorder, a place where the cosmos might keep its quietest truths. As the holographic idea grew, physicists began searching for concrete ways information might cling to the surface of a black hole. One proposal arrived with a gentle, almost poetic name: soft hair. Not hair in any literal sense, but faint, delicate features, tiny ripples in the gravitational or electromagnetic field surrounding a black hole. These ripples could, in principle, carry traces of whatever has fallen in, giving the black hole a subtle memory of its past. Imagine the event horizon again, smooth and quiet, but now with the soft suggestion of texture, patterns far too fine for the eye to see, yet present in the way space-time curves and fields fluctuate. When an object falls inside, it doesn't leave a mark like a footprint in sand. Instead, it may create a shift in these fields, a change so subtle that it was long overlooked. These tiny adjustments are what physicists call soft hair. To understand it, think of the surface of a still pond. When a leaf touches it, the water seems to remain smooth, but beneath that stillness, gentle ripples travel outward. They fade slowly, carrying a faint memory of the leaf's shape and motion. Soft hair is the gravitational equivalent of those ripples, delicate patterns spreading across the horizon, patterns that might encode information without breaking the smoothness of the black hole itself. As you breathe slowly, imagine these ripples flowing outward across the dark boundary, whispering details of atoms, molecules, and light that once approached the black hole. If this idea is correct, the black hole is no longer a perfectly featureless object. It becomes a surface rich with faint structure, soft enough not to disturb relativity's demands, yet intricate enough to store information. This possibility does not solve the paradox entirely, but it provides a bridge, a way for information to persist near the horizon instead of disappearing into the singularity's unknown depths. When the black hole evaporates through Hawking radiation, the soft hair might help guide the information outward, encoded subtly into the particles that escape. Whether this encoding is clear, chaotic, or beautifully ordered remains uncertain. But the idea itself is comforting. The universe might have hidden pockets of memory, concealed in ripples too fine to notice yet powerful enough to preserve the story of every falling thing. Soft hair is a reminder that nature often hides complexity beneath apparent simplicity. What looks smooth from afar may contain quiet layers of structure, like a calm sky filled with faint currents of wind, and so the paradox loosens a little, not solved, but reshaped, as though the universe is offering a quiet hint, a soft ripple, pointing toward deeper understanding. As the search for answers continued, physicists looked even deeper, beneath particles, beneath fields, beneath the very fabric of space-time. In that depth lies string theory, a framework that suggests everything in the universe may be made of tiny, vibrating strands of energy. These strings, according to the theory, produce all the particles and forces we know, depending on the frequency and pattern of their vibrations. And in the quiet realm of black holes, these strings may hold the key to where information truly goes. Imagine space-time not as a smooth sheet, but as a woven tapestry made of threads thinner than anything we can imagine. Each particle is a vibration along one of those threads. Each interaction is a dance between strings. When something falls into a black hole, the string theory picture suggests that nothing truly disappears. Instead, the vibrational pattern simply shifts location, absorbed into the tangled network of strings that make up the black hole's interior and horizon. In this view, the black hole is not a featureless void. It is a dense, complex state of strings, all tightly wound by gravity. The information carried by falling matter becomes embedded in these vibrational modes, preserved in ways too subtle for classical physics to recognize. And when the black hole emits Hawking radiation, the outgoing particles may carry hints of those internal string vibrations, faint signatures that allow information to escape without violating quantum principles. As you rest, imagine these strings humming softly, like the quiet plucking of distant harp strings in a vast, dark chamber. Each note carries meaning, each vibration holds memory. Even if the black hole shrinks, even if it evaporates completely, those vibrational patterns might transform rather than vanish, passing their details into the radiation one subtle bit at a time. String theory also offers a comforting idea, that the interior of the black hole may not be the unknowable abyss it appears to be. Instead, it could be a network of strings whose properties reflect the information crossing the horizon. The universe might be more unified than it seems, blending gravity and quantum mechanics into a single harmonious framework, one where information is never lost, only translated into new forms. Whether string theory is the final answer remains uncertain, but its imagery provides a soft, poetic way to think about the paradox. Nothing is erased, nothing is forgotten, everything becomes vibration, carried forward through the deep structure of space-time. Let that thought settle gently. Beneath the darkness, beneath the horizon, beneath even the concept of particles, the universe may be singing. And encoded in that song may be every story a black hole has ever swallowed. From soft hair and vibrating strings, we drift now into one of the most quietly transformative ideas in modern physics, the suggestion that our entire universe might behave like a hologram, not a projection in the everyday sense, but a profound principle, that all the information inside a region of space can be fully described by the information stored on its boundary. For black holes, this idea becomes especially powerful if the horizon truly carries the information of everything that falls inside. Then perhaps nothing is ever lost at all. Imagine holding a holographic plate in your hand. The surface looks flat, simple, unremarkable. but when illuminated in the right way, a full three-dimensional image appears, rich with depth and detail. The information that forms the image is stored on the surface, not within the volume it represents. Now imagine the event horizon as such a plate, a dark, curved surface carrying the full history of everything that has crossed it. What lies within the black hole becomes secondary. The surface itself becomes the storyteller. This is the essence of the holographic principle. The boundary holds the memory. The inside is a kind of projection, a reflection of what the boundary encodes. If this is true, then the old worry that information falls into a singularity and vanishes may be misplaced. The singularity might not need to store anything at all. The horizon, the edge, the surface, the quiet boundary may already contain everything the universe refuses to forget. As you breathe softly, imagine this principle extending beyond black holes. Some physicists propose that our entire universe may function holographically, that everything we experience in 3 dimensions is described by information written on a vast cosmic boundary. It is a gentle, mind-opening idea, not meant to confuse, but to show how deeply interconnected things might be. The space around you, the distant galaxies, the quiet dark between stars, all could be reflections of information woven along a far-off edge. In this picture, black holes no longer threaten the universe's rules. Their information does not vanish. It simply becomes encoded where we did not think to look. And as the black hole evaporates, the horizon shrinks, releasing its stored information gradually, subtly, through Hawking radiation. Nothing is lost, only translated into a different form. You do not need to visualize the mathematics behind this idea. Let it drift through your thoughts like a soft wave. The cosmos may be deeper than it appears. Surfaces may hold secrets. Boundaries may know more than the interiors. And perhaps the question of information loss becomes not a paradox, but a quiet reminder that the universe often hides its truths in places we do not expect. As we drift deeper into the paradox, another quiet idea begins to glow at the edges of our understanding. Quantum entanglement, the strange connection that allows particles to share information instantly, no matter how far apart they travel. Entanglement is delicate, invisible, and profoundly fundamental. It is the universe's way of weaving relationships between particles, linking their states as if they share a single heartbeat. Imagine 2 particles created together. They separate, drifting into different corners of space, yet their properties remain intertwined. Touch one, and the other responds instantly and silently, as though they are still side by side. This connection does not send signals. It does not break the rules of relativity. It simply reflects the deep unity built into the fabric of quantum mechanics, a unity that might help explain how information survives near a black hole. As something falls toward the event horizon, its particles are entangled with countless others in the universe. If the falling particle disappears completely inside the black hole, what happens to the entanglement it shares with the outside world? Does the bond break? Does it persist? Does it rearrange itself into new connections we cannot yet picture? These questions led physicists to imagine that entanglement itself might serve as a kind of bridge, a quiet thread linking the inside and outside of the black hole. Some theories propose that every piece of information falling into a black hole becomes entangled with the particles that escape through Hawking radiation. The radiation, then, is not featureless. It is part of a vast network of links, carrying subtle echoes of the information inside. These echoes are too faint for us to decode today, but in principle, they might allow the universe to preserve its memory without violating any physical law. There is even a poetic notion, often summarized in the phrase ER sken EPR, suggesting that entanglement and wormholes might be 2 sides of the same phenomenon. In this view, entangled particles are connected by tiny geometric bridges. not tunnels you could travel through, but threads woven into space-time itself. If this idea is true, then the interior of the black hole and the outgoing radiation are not separate realms. They are parts of the same connected structure. As you relax into this thought, imagine entanglement as a soft web stretched across the cosmos, visible but ever-present, binding distant corners of reality into a single, flowing whole. Information might never be trapped or destroyed. It may simply travel along pathways we do not yet understand, carried through the quiet geometry of quantum relationships. Let this idea settle gently. The universe is more connected than it appears. Even in darkness, threads of information may continue to shimmer. As physicists followed the threads of entanglement deeper into the paradox, they encountered an unexpected tension, one that led to the birth of a bold and unsettling idea known as the firewall. It stands in sharp contrast to the peaceful picture we've held until now. In the classical view, the event horizon is calm and smooth. Crossing it feels no different than drifting through quiet darkness. But quantum mechanics, with its intricate web of entanglement, suggests something far less serene may occur. The puzzle arises when we try to satisfy three principles at once: that information is not destroyed, that physics looks normal to someone falling into a black hole, and that Hawking radiation is entangled with the interior. These three ideas cannot all be true simultaneously, at least not within our current understanding. Imagine standing at the edge of the horizon in thought. The classical picture tells you nothing unusual will happen. Gravity will feel gentle, the crossing will be smooth. Yet the quantum picture, under certain assumptions, suggests that the entanglement between inside and outside becomes inconsistent at this boundary. And when entanglement is forced to break suddenly, something dramatic occurs. The horizon ignites into a highly energetic surface, a firewall. In this scenario, the boundary is no longer soft or invisible. It becomes a wall of intense radiation, destroying anything that attempts to cross. The peaceful horizon dissolves. The smoothness of space-time collapses. The long-held belief that nothing special happens at the horizon is shattered. As you breathe gently, let this idea settle without alarm. The firewall is not a physical prediction most physicists accept. It is a philosophical warning, a sign that our current theories do not mesh together seamlessly. The firewall paradox tells us that something in our understanding must shift. Either gravity, quantum mechanics, or the nature of entanglement needs a new interpretation. Some researchers argue that the event horizon cannot host a firewall. It would break the very spirit of general relativity. Others believe the firewall reveals a deep truth, that space-time itself may reorganize near the horizon in ways we have yet to uncover. And still others think the problem disappears entirely once we adopt a more complete theory of quantum gravity. The debate continues softly, like murmurs in a distant hall of thought. No shouting, no urgency, just careful reflection. The firewall is not meant to frighten. It is meant to illuminate the limits of our knowledge, reminding us how much mystery remains hidden in the quiet folds of space-time. Tonight we hold the idea gently, not as a conclusion, but as a stepping stone, a signpost pointing toward deeper layers of the paradox, where new possibilities begin to emerge. To feel the weight and the beauty of the firewall idea, imagine the event horizon not as the smooth, silent boundary we've grown familiar with, but as something alive with energy. In this alternate picture, the horizon shimmers with quantum heat, burning away anything that touches it. No gentle crossing, no quiet descent. Instead, a sudden blaze of information, transformed violently the moment an object arrives. It is a dramatic contrast to the serene landscapes we've drifted through, and that contrast reveals something important about our theories. In classical general relativity, the horizon is perfectly calm. A falling astronaut notices nothing unusual. Space-time curves but gently, like a smooth wave beneath a floating leaf. Yet when we introduce quantum entanglement and demand that information must survive, the mathematics begins to strain. The entanglement between interior and exterior states can't both remain intact and allow a peaceful crossing. Something must give. The proposed solution, the firewall, is a horizon that breaks the calm. It becomes a place where quantum fields erupt, severing entanglements and releasing enormous energy. But as striking as this idea sounds, most physicists hesitate to embrace it. It violates a cherished principle called the equivalence principle, which says gravity should feel smooth to someone in free fall. A firewall violates that simplicity, turning the black hole into a boundary of violent transformation. As you breathe softly, picture these two horizons, one calm, one fiery. Side by side, they illustrate a deeper truth, that our current understanding of the universe contains contradictions we have not yet reconciled. The firewall is not a prediction, it is a symptom of unfinished physics, a gentle reminder that gravity and quantum mechanics are speaking different languages at the edge of a black hole. Some researchers argue that the fire never truly forms because information is stored on the horizon itself, avoiding the need to break entanglement. Others believe the horizon remains smooth because quantum gravity subtly reshapes the interior structure, preserving both information and the calm experience of falling. A third group suggests that our picture of space-time may need to shift entirely, making room for new physics that dissolves the conflict naturally. As you lie back, let the image drift away. The purpose of the firewall debate is not to alarm, but to illuminate. It shows how deeply we are still learning, how the edges of knowledge glow with tension, the way a distant horizon glows with fading light. Whether the horizon is calm or fiery, the deeper truth is this: the universe is nudging us toward a more complete understanding, one that honours both gravity's smooth flow and quantum mechanics' insistence on memory. For now, the horizon remains a place of possibility, not fire, not silence, but mystery inviting us forward. As we move past the tension of firewalls and conflicting theories, a gentler metaphor begins to take shape. The idea of the black hole not as a destroyer, not as a silent vault, but as a storyteller. In this view, nothing that falls in is erased. Instead, it is transformed, rewritten, and re-expressed in ways we are only beginning to imagine. A black hole becomes a kind of cosmic author, taking the details of matter and light and weaving them into new patterns, perhaps encoded in the horizon, perhaps carried away by Hawking radiation, perhaps held in the shifting structure of space-time itself. Imagine matter falling inward, a grain of dust, a passing photon, a cloud of gas drifting like a soft mist. In our classical picture, the moment these objects cross the horizon, their stories end. But in a quantum universe, endings are seldom so abrupt. The information they carry, their story, may continue, written into the horizon as delicate patterns, or into the radiation as subtle correlations, or into the quantum structure of space-time in ways too fine for our current instruments to detect. This perspective softens the paradox. Instead of losing information, the black hole may simply rewrite it. The original form disappears, but the essential details persist, transformed into new language. Much like how a tree becomes smoke and ash without losing the information contained in its atoms, an object falling into a black hole may become something else entirely. A pattern smeared across the horizon, a modification to entanglement links, a tiny shift in the geometry of space-time. As you rest, imagine the black hole humming softly with these stories, not in sound, but in the quiet patterns of its fields and radiation. Each particle that escapes carries a faint echo, a whisper of the black hole's past, not a clear message but a subtle correlation, like the rhythm of waves revealing the shape of the wind that once stirred them. This view is gentle, poetic, and scientifically plausible. It allows the black hole to preserve the universe's most sacred rule: that information cannot be destroyed, while maintaining the calm horizon predicted by general relativity. The paradox does not vanish, but it loosens, opening space for a more unified understanding. And in this softened picture, the black hole is no longer a graveyard. It is a storyteller, a transformer, a custodian of cosmic memory, reshaping the details of what it consumes and releasing them slowly, patiently, in ways we have not yet learned to read. Let that idea settle like a quiet exhale. Nothing falls into silence. Everything becomes part of a larger, quieter tale. As we drift further into the subtle layers of the paradox, we return to an idea already whispered earlier: quantum hair, faint, intricate structures that might decorate the horizon of a black hole. These are not physical strands or visible markings, but delicate variations in the field surrounding the black hole, storing information in patterns far too subtle for classical physics to perceive. We revisit this idea now with deeper clarity, because the more we explore the paradox, the more quantum hair appears not as a curiosity, but as a meaningful bridge between what falls in and what radiates away. Imagine the event horizon again, not smooth and featureless, but shimmering gently with microscopic detail. Ripples woven from quantum mechanics, too fine for the eye, too delicate for any classical instrument, yet capable of carrying echoes of everything the black hole has consumed. Quantum hair proposes that even though black holes look simple from a distance, their surfaces may secretly hold a vast tapestry of information encoded in field variations and gravitational subtleties. When a particle or a photon falls into the black hole, it subtly alters these fields. The horizon shifts, ever so slightly, as though the black hole takes a breath and adjusts itself to the new presence. These adjustments may be small, unimaginably small, but they may hold the essence of the information that would otherwise appear lost. If quantum hair exists, the black hole becomes more like a memory device than a void. As the black hole evaporates through Hawking radiation, the presence of quantum hair suggests that the outgoing radiation is not purely random. Instead, the radiation could carry faint correlations shaped by the horizon's quantum details. Not enough for us to decode today, but enough for the universe to preserve its own rules. The story that fell inside is not erased. It is smeared, transformed, and gradually released in a form we have not yet learned to decipher. As you breathe deeply, picture the horizon as a dark lake at night. On its surface, faint ripples move outward, almost invisible, yet carrying information about the raindrops that disturbed it. Quantum hair offers a similar image. Shadows of memory spread across the horizon, gentle and hidden, but present all the same. Some physicists debate whether quantum hair is enough to solve the paradox fully. Others see it as part of a larger tapestry of ideas: holography, entanglement, quantum gravity, all converging toward a future understanding. But the essence remains calming. The black hole may not be as forgetful as classical theory once suggested. Let this thought settle softly. Even in darkness, the universe may keep quiet traces of everything it touches, delicate signatures woven in the fabric of space-time. To feel the next layer of the paradox, imagine two black holes spiraling toward each other in the deep quiet of space. For billions of years they drift apart, barely interacting with anything. But then, drawn by mutual gravity, they begin to circle slowly at first, then faster still, until they collide in a moment of immense yet silent power. Nothing in the universe hears this collision directly. Sound cannot travel through space, but space-time itself trembles, sending out ripples we know as gravitational waves. These waves were first detected in 2015 by LIGO, and each detection since has offered a kind of cosmic whisper, a faint vibration that tells us two giants met, merged, and became one. But beyond confirming their existence, these waves hint at something even more subtle. They may carry echoes of information stored on the horizons of the black holes before the merger. Imagine the horizons touching like the surfaces of two dark oceans. When they collide, their shapes ripple, stretch, and rearrange. These vibrations, called quasi-normal modes, ring out like the fading tones of a struck bell. Classical physics predicts these tones precisely, defining how the new black hole settles into its final, smooth form. But if quantum hair or holographic structures exist on the horizons, then the vibrations might deviate ever so slightly from the classical predictions. They might carry gentle distortions, faint traces of information about what each black hole had swallowed before the merger. Some researchers call these subtle distortions echoes, because they would appear as tiny repetitions in the gravitational wave signal, arriving fractions of a second after the main ring down. Not loud enough to stand out sharply, not clear enough to decode as words, but soft patterns, like ripples reflecting from the curved walls of a vast chamber. These echoes, if they exist, would be the first observational hint that black holes carry more structure than the no-hair theorem allows, and that information may indeed linger on or near the horizon. As you breathe gently, imagine those waves travelling across billions of light years, stretching and squeezing space-time as they pass. When they reach Earth, the tremors they cause are smaller than a fraction of the width of an atom, and yet, within that tiny motion might lie clues about the black hole's memory, clues about whether the universe truly keeps track of every particle, every quantum state, every forgotten moment swallowed in the dark. We cannot hear these echoes with our ears, but the detectors can feel them. And if one day we confirm their presence, it would mean that black holes are not silent tombs but vibrating storytellers, revealing fragments of information through the soft music of space-time. Let that image rest with you. Two giants merging, the universe shaking, and in the fading tremors, perhaps the quiet echoes of everything they once consumed. As our journey grows quieter and deeper, we arrive at one of the most delicate ideas in theoretical physics, the possibility that the event horizon is not perfectly smooth at all, but instead flickers with a subtle, frothy structure known as space-time foam. This concept, rooted in quantum gravity, proposes that at the smallest possible scales, space-time does not behave like a continuous fabric. Instead, it trembles, fluctuates, and reshapes itself in ever-changing patterns too tiny for ordinary physics to notice. Imagine looking at the surface of a calm sea from far away. It appears smooth, unbroken, serene, but up close, at the scale of droplets and tiny ripples, the surface is alive with motion. Quantum mechanics suggests that space-time behaves similarly. From afar, the event horizon looks like a perfect dark curve. But at the Planck scale, far smaller than any atom, it may froth with microscopic fluctuations, bubbling in and out of existence. These fluctuations, this foam, might provide a path for information to survive. When matter falls into the black hole, the foam could shift in response, encoding details of the infalling particles in patterns far too fine to disturb general relativity's smooth picture. Even though the horizon appears featureless to classical physics, its quantum structure might be endlessly intricate, like a tapestry whose threads are woven from vibrating space-time itself. As you breathe softly, imagine the horizon shimmering with these quantum fluctuations, not violently but gently, like the faint sparkle seen on water under moonlight. Each ripple is minuscule, yet potentially meaningful. Each fluctuation might store a tiny piece of information, preserving the universe's memory in ways we cannot yet observe. And as the black hole evaporates through Hawking radiation, this foam could subtly guide how the information escapes, ensuring nothing is truly lost. The idea of space-time foam also aligns with a deeper intuition, that the universe, at its smallest scales, is not rigid but playful, not smooth but dynamic. Even gravity, which feels so steady in our daily lives, may fluctuate in invisible ways that carry traces of the past. Some physicists doubt that foam alone can solve the paradox, while others believe it may be a crucial ingredient, one piece in a larger puzzle that includes holography, entanglement, and quantum fields. But whether or not foam provides the full answer, its presence reminds us that the universe's foundations are richer and more intricate than they appear from a distance. Let this thought drift gently. Even the darkest, smoothest horizons may shimmer with unseen structure, a quiet, ever-changing dance at the edge of space-time, carrying whispers of everything the black hole has ever touched. As we gather the many threads of holography, entanglement, quantum hair, and space-time foam, a gentle realization begins to form. The information paradox is more than a scientific puzzle. It is a mirror the universe holds up to us, reflecting not only the limits of our theories, but the limits of our imagination. Black holes sit at the intersection of gravity and quantum mechanics, two frameworks that describe reality with extraordinary accuracy, yet refuse to fully agree at the horizon. And in their disagreement, we find ourselves staring into the deeper question of how the universe truly works. Imagine standing at the edge of a quiet lake at dusk. The water reflects the sky, but the reflection is not the sky itself. It is a hint, a suggestion, a distorted image revealing as much about your viewpoint as about the world it mirrors. The information paradox behaves in much the same way. It reflects both our understanding and our uncertainty, showing us where our theories shine and where they falter. When we ask, where does the information go? We're not only asking about black holes, we're asking whether the universe keeps its story coherent, whether cause leads cleanly to effect, whether the past can be erased or whether it is woven permanently into the fabric of time. The paradox mirrors our desire for order, meaning continuity. And perhaps it reminds us that the unknown is not a flaw in nature, but an invitation to expand our vision. As you breathe softly, imagine this paradox as a calm, unmoving surface, a place where two great theories cast their reflections. On one side is general relativity, smooth and elegant, describing gravity with flowing curves. On the other is quantum mechanics, intricate and lively, describing particles with probabilities and entanglements. At the horizon, their reflections overlap, distort and ripple, revealing the places where each theory alone is incomplete. The paradox also mirrors something human, our own boundaries of understanding. Just as the event horizon hides what lies inside, our minds often approach the edges of comprehension, places where intuition fades and deeper insight is needed. Yet these boundaries are not failures, they are thresholds, invitations to grow, to imagine beyond what we know. In this gentle way, the information paradox becomes more than a scientific problem. It becomes a meditation, a reminder that mystery is not an enemy of knowledge but its companion, that the cosmos, like consciousness, contains depths that unfold slowly, inviting patience rather than certainty. Let this reflection settle. The paradox is not only about black holes, it is about us, and the quiet horizons where understanding begins to stretch into wonder. To deepen our sense of the paradox, we return now to the beginning of every black hole's life, the collapse of a massive star. Understanding where a black hole comes from helps us appreciate how much information it inherits, how much history it contains, and how strange it would be for all of that to simply disappear. A black hole is not born empty. It is born from a star that lived, burned, fused, and evolved over millions of years. Imagine a star many times the mass of our Sun. For most of its life, it shines steadily, balancing gravity's inward pull with the outward pressure of nuclear fusion. Deep in its core, hydrogen becomes helium. Helium becomes heavier elements, and each fusion step writes new information into the star structure. Temperatures, densities, magnetic fields, patterns of convection. These details fill the star like pages in a vast cosmic diary. But eventually, the star exhausts its nuclear fuel. Without the outward pressure of fusion, gravity takes hold. The core collapses in a fraction of a second. Outer layers rebound in a supernova, scattering newly forged elements across space. What remains is a core so dense that atoms cannot support it. Electrons merge with protons, neutrons themselves begin to fail, and finally, gravity wins completely. The collapse continues until space-time curves so sharply around the core that it forms an event horizon. In that moment, the star's long history vanishes from view. All its information, its internal layers, its movement, its temperature profile, its chemical structure, slips behind the horizon. Classical general relativity tells us that only three numbers remain: mass, spin, and charge. The rich, detailed story of a star becomes a black sphere defined by just a few parameters. This enormous compression of information into a seemingly simple object is part of what makes black holes so mysterious. As you breathe gently, imagine that star's final light fading, its structure folding into darkness. The paradox grows sharper. If the universe loses all access to the star's information, does that mean the star's story is gone forever? Does its long life, its cycles of fusion, its inner currents and magnetic storms simply cease to exist? Quantum mechanics tells us they must not. Somewhere, somehow, the details must persist, encoded in the horizon, stored in space-time's subtle structure, or woven into the radiation that escapes over trillions of years. The fallen star becomes a question mark written into the cosmos, challenging us not to forget its intricacy. Let this idea rest with you. A black hole is not just an end, it is a container of stories, and the fate of those stories lies at the heart of the information paradox. To understand the strange role black holes play in the universe and in the information paradox, we must step deeper into the realm of relativity, where time and light behave in ways that defy ordinary intuition. Near a black hole, space-time is so sharply curved that even the flow of time becomes distorted. What feels like moments to a falling observer may appear as centuries to someone watching from afar. And light, the fastest thing in the universe, finds its path bent, stretched, and pulled into quiet spirals. Imagine drifting toward a black hole in thought. At first, everything seems normal. The stars shine. The background hum of space feels unwavering. But as you approach the horizon, time itself begins to slow. Your heartbeat still feels steady within your own frame of reference, but to the outside universe, your motions stretch into long, lingering moments. Every gesture becomes drawn out. Every second feels like an eternity when viewed from afar. This slowing of time is not an illusion. It is the fabric of space-time bending under the weight of gravity. The closer you come to the horizon, the more extreme the effect becomes. From the outside, it appears as though you never truly cross the boundary. You fade, you redden, you linger at the threshold, frozen in time. At the same moment, light undergoes its own transformation. Photons that once raced freely now bend inward, unable to maintain their straight paths. Their wavelengths stretch, sliding into deeper shades of red. Eventually, near the horizon, the light becomes so stretched that it effectively disappears. This bending and fading of light is why black holes appear so dark, not because they are evil or violent, but because the rules of space-time itself gently guide light away from escape. As you breathe softly, imagine these distortions not as harsh or terrifying, but as part of a grand, smooth choreography. Everything moves according to the curves of space-time. Light leans inward like a wave, pulled by an unseen tide. Time stretches like a long, deep exhale. These distortions reveal the immense gravitational power of a black hole, and they also deepen the information paradox. If light is stretched into near invisibility, and if time slows to a standstill from the outside view, how can the universe possibly track the information falling inward? To an observer watching from far away, the information appears locked indefinitely at the horizon, fading into red light and then into silence. But to the object itself, the crossing is quick and uneventful. Two realities coexist, each valid, each incomplete. Let this contrast drift gently through your thoughts. Near a black hole, the rules of time and light change not with violence, but with quiet inevitability, revealing just how deeply gravity shapes the universe's memory. If you let your thoughts drift across the vast timeline of the cosmos, black holes reveal a quality unlike any other object in the universe: patience. They do not burn with urgency like stars. They do not shatter in sudden bursts like supernovae. Instead, they wait, they hold, they persist. A black hole can remain unchanged for billions, even trillions of years, influencing everything around it with silent gravity, yet expressing no haste of its own. Imagine a black hole resting in the centre of a distant galaxy. Stars spin around it like lanterns in a quiet dance. Clouds of gas drift slowly by, some spiralling inward, some escaping into deeper space. The black hole sits at the core, motionless to the eye, yet shaping the galaxy's structure with its deep gravitational well. It doesn't consume everything around it. Most matter never comes close. The black hole simply waits, allowing the universe to move at its own rhythm. This patience plays a key role in the information paradox. Because black holes live so long, they can collect vast histories. A single black hole might swallow the remains of stars, planets, gas clouds, and even stray photons over unimaginable stretches of time. Each event adds to the information hidden behind the horizon. The black hole becomes a quiet archive, one that may outlive everything around it. But this patience creates tension with quantum mechanics, which insists that information cannot be destroyed. If the black hole holds on to details for trillions of years, only to evaporate into featureless radiation, then where does that long-held information finally go? How does the universe safeguard its own record if memory sits behind a horizon that eventually disappears? As you breathe softly, imagine the black hole as a deep, still pool. Objects fall in rarely, but when they do, the pool accepts them without ripple or sound. Over time, the pool accumulates stories, not in visible layers, but in the structure beneath the surface. The information paradox asks whether, when the pool eventually dries, the stories evaporate too. Yet the black hole's patience gives physicists time as well. Time to think, time to imagine new theories, time to search for subtle clues in gravitational waves and cosmic observations. The long lifespan of black holes mirrors the slow unfolding of our understanding. Nothing about this mystery demands urgency, it simply invites contemplation. Let this thought drift gently with you. Black holes are not hurried objects. They are the universe in its most patient form, holding secrets for ages, waiting quietly for us to discover how their stories continue. To understand why the information paradox matters so deeply, we must look at information not as an abstract mathematical quantity, but as a form of cosmic memory. Every particle, every wave, every fluctuation in the universe carries traces of where it has been and what it has interacted with. These traces form a vast interconnected record, a quiet ledger maintained by the laws of physics themselves. Imagine the universe as an enormous library. Every event writes a new line. Every collision adds a new chapter. The motion of stars, the shimmer of particles, the gentle rippling of space all contribute to this unfolding chronicle. Even the smallest quantum states are part of the story, encoded in the wave functions that describe their behaviour. In this sense, information is not just data, it is the universe remembering itself. Quantum mechanics goes further, insisting that this memory must be perfect. Even when particles scatter, decay, or transform, the total information describing the system cannot be lost. It may become scrambled beyond recognition, but it remains somewhere, conserved by the deep structure of reality. This principle, known as unitarity, is one of the cornerstones of modern physics. It keeps the universe consistent, predictable, whole. But black holes challenge this picture. When something falls into the event horizon, the information seems to vanish behind the boundary, and when the black hole eventually evaporates into Hawking radiation that appears random and devoid of detail, the cosmic memory appears to vanish as well. This is why the paradox strikes at the foundation of physics. It is not merely about matter disappearing. It is about the universe losing track of its own history. As you breathe gently, imagine information as patterns of light drifting across the cosmos. These patterns do not disappear when the light dims. They spread, scatter, transform, and persist in new forms. A black hole seems at first glance to defy this rule. It appears to take in patterns and return only randomness. But many physicists believe this is an illusion, that the patterns survive in hidden ways, encoded on the horizon, tangled through quantum fields, or released gradually through subtle correlations in Hawking radiation. To hold this idea is to appreciate the universe not as a place of destruction, but of preservation. Even when stars collapse and matter falls into darkness, the underlying memory may endure. The cosmos does not forget. It only reshapes its stories. Let this thought rest with you like a soft whisper. Information is not fragile. It is woven into the fabric of reality. And even the darkest places in the universe may be keepers of memory, not thieves of it. For decades, black holes existed only in equations and imagination. Their horizons were abstractions, their shadows pure theory. But in 2019, the universe offered us a quiet gift. The first ever image of a black hole, captured by the Event Horizon Telescope, a planet-sized network of observatories working together as one. For the first time, humanity looked directly at the edge of a black hole's darkness, and the image revealed more than physics. It revealed a feeling. Imagine standing before that image, a glowing ring of light embracing a dark centre. The ring forms because light, bent by intense gravity, spirals around the black hole before escaping toward us. The dark centre, the shadow, is not the black hole itself, but the region from which no light can reach us. It is the closest we have ever come to seeing an event horizon. This image did not solve the information paradox, but it deepened our relationship with it. Ideas that once floated in theoretical space suddenly had a face, a shape, a radiant outline. The black hole in the image, located in the galaxy M87, is enormous, billions of times the mass of our Sun, yet we captured its silhouette with breathtaking precision. The glow around it is gas heated to incredible temperatures, swirling just outside the event horizon. The light carries the signature of gravity at its strongest, bending and looping before breaking free. As you breathe softly, imagine the journey of that light. It left the region near the black hole long before humans existed, travelling across 55 million light-years before reaching Earth. Each photon carries not information about what fell inside, but about the environment just outside the horizon, the glowing dance of matter at the edge of no return. The image is a portrait of gravity shaping light, a moment where theory meets vision. The Event Horizon Telescope also offers hints about deeper questions. The shape and brightness of the ring may contain subtle deviations if the horizon has structure. If quantum hair, holographic patterns, or space-time foam alter the gravitational field. These deviations are beyond our current sensitivity, but future telescopes may reveal them, giving us a way to test theories about information preservation. In this sense, the black hole becomes not just an object, but a laboratory. a natural experiment crafted by the universe itself. Each observation brings us closer to understanding how horizons store, distort, or release information. The paradox, once confined to chalkboards and thought experiments, now glows in orange light captured by global collaboration. Let this image settle gently into your mind. A ring of fire surrounding a darkness that is not empty, but full of questions. Quiet, patient, waiting for us to listen. The silhouette of a black hole, that soft, circular darkness surrounded by a glowing ring, reveals more than a shape. It reveals the quiet dialogue between shadows and light, a conversation written in curved space-time. Even though we cannot see what lies beyond the event horizon, the light that circles it tells a story. It bends, stretches, and loops around the black hole many times before escaping, carrying with it the imprint of gravity's deepest pull. Imagine light as a traveller who approaches the black hole cautiously. Some photons pass by unharmed, continuing their journey through space. Others are pulled into curved paths, spiralling around the horizon in orbits called photon rings. Some make one loop, others 2 or 3, before escaping to distant observers like us. With each loop, the light picks up more information about the black hole's geometry, its mass, its spin, its orientation, all encoded in the delicate brightness of the ring. The shadow itself is not a physical surface, but an absence, a region where light cannot escape to reach us. It is a map of space-time's curvature, a window into the strength of gravity near the horizon. The shape of this shadow is predicted by general relativity, and so far, the predictions match what we observe. But tiny deviations, if we someday detect them, could reveal quantum structures on the horizon. They could hint at holographic surfaces, space-time foam, or traces of quantum hair shaping the light that moves around the black hole. As you breathe gently, imagine this: light circling in silence, tracing paths so delicate that a single photon may take years to complete its orbit. It emerges not with words, but with measurements, angles, intensities, polarization, all subtle clues about the structure of the horizon. The black hole does not speak, yet the light around it carries messages encoded by gravity's hand. These messages give us confidence that the information paradox is not a dead end but an open door. If the horizon truly has fine structure, the shadow may hold hints of it. If information survives, the patterns of light may someday reveal how. Even the brightness of different regions in the ring offers insight into magnetic fields, gas flows, and the behaviour of particles near the boundary of no return. In this sense, shadows are not empty. They are a canvas upon which the universe paints with bent light. They show where information hides, where physics stretches, and where mysteries deepen. They remind us that darkness and illumination are partners, each shaping the story of the other. Let this thought settle softly. Even in the deepest shadows, the universe finds ways to let its light speak, quietly, beautifully, and truthfully. In the quiet glow around a black hole's shadow, there is a deeper realization waiting to unfold. When we observe these distant giants, the universe is, in a sense, watching itself. Light that spent millions of years circling the horizon reaches our telescopes and becomes part of human understanding. Waves of space-time that ripple from merging black holes pass through detectors on Earth, imprinting their patterns into our instruments. Information, once hidden at the edge of gravity, becomes part of our collective awareness. Imagine this process gently. A beam of light leaves the swirling gas near a black hole, carrying with it subtle details about temperature, motion, and curvature. It travels through intergalactic space, untouched and uninterrupted, drifting like a silent messenger across unimaginable distances. When it finally arrives on Earth, it touches a sensor, a dish, an antenna, a delicate receiver frozen high on a mountaintop. and the universe's message is written into our machines. A record is made. A data point is stored. A fragment of cosmic memory becomes part of human memory. The same holds true for gravitational waves. These ripples in space-time begin as vibrations in the fabric of reality itself. When two black holes merge, space-time rings like a struck bell. Those waves travel outward, passing through galaxies, through clusters, through dust and darkness, until after billions of years they sweep through Earth as faint tremors. Our detectors stretch by less than a fraction of an atom. Yet within that tiny motion is encoded the story of two giants spiraling together. As you breathe softly, imagine this gentle exchange, the universe expressing its history through light and waves, and humanity listening with quiet patience. We're not separate from the cosmos we study. Our observations are part of its unfolding, part of the grand cycle of information flowing from creation to awareness. In learning about black holes, we become a chapter in their story. This realization softens the information paradox further. Perhaps information is not simply something the universe holds within itself. Perhaps information is something the universe shares, through radiation, through gravity, through observation. When we capture an image of a black hole or detect its waves, we participate in the cosmic flow of memory. Even if some details remain hidden behind horizons, others are revealed in the patterns that reach us. In this gentle dance, the universe grows more self-aware, not through consciousness in the human sense, but through the continuity of information passing from one part of space-time to another. A black hole emits light shaped by its gravity. That light reaches us. We interpret it, and in that act the cosmos reflects upon itself. Let this thought rest like a slow exhale. Every observation is a connection. Every measurement is a meeting point between our minds and the universe's memory. As we drift into the philosophical currents of tonight's journey, the information paradox invites a gentler question. What is truth in a universe that is always changing? Black holes challenge the idea that truth is fixed, permanent, and easily retrievable. They blur the boundary between what is known and what is hidden, and yet in this blurring they reveal something important, that truth in a cosmic sense may not be a single fact, but a pattern, a continuity, a transformation. Imagine standing at the edge of a vast desert at twilight. The landscape changes with every gust of wind. Dunes shift, shadows move, footprints soften and disappear, yet the desert itself remains, its essence unchanged even as its details transform. Truth in the universe behaves similarly. The details of matter and energy shift endlessly, falling into stars, collapsing into black holes, radiating outward in waves of light, but the underlying laws remain stable, preserving the deeper patterns even when the surface changes. The information paradox tests this principle. If information appears to vanish inside a black hole, does the universe break its own promise of consistency? Does the story of reality gain missing pages? Or does truth simply reorganize itself in ways we cannot yet read? As you breathe quietly, consider that information may not be about preserving static facts. It may be about preserving relationships, the way particles interacted, the way states evolved, the way quantum fields intertwined. Even if those relationships are transformed beyond recognition, the universe may hold them in new forms, encoded in the horizon, carried through entanglement, woven into Hawking radiation. Much like memories in the human mind, cosmic truth might persist not as a perfect copy of the past, but as a transformed imprint, shaped by experience, altered by time, yet not erased. The universe does not stand still. Its truths ripple, adapt, and reorganize. And black holes, rather than destroying truth, may be catalysts that reshape it. Physics seeks clarity, but the paradox encourages humility. It reminds us that truth at the cosmic scale may not always align with intuition. We are used to thinking that something is either preserved or lost, visible or hidden, present or gone. The universe may be more fluid than that, more like a river that retains its identity even as every drop of water changes. Let this realization settle softly. Truth in a changing universe is not about permanence. It is about continuity. The gentle persistence of patterns even as their forms shift. And perhaps the information paradox is not the universe breaking its rules, but inviting us to discover deeper ones. As the night deepens and our journey slows, the information paradox begins to feel less like a scientific problem and more like a gentle meditation, a space where curiosity softens, where questions are allowed to remain open, and where uncertainty becomes a place of rest rather than tension. The paradox, in its quiet way, offers an invitation to sit with the unknown, to breathe with it, and to let the mind drift into wider forms of understanding. Imagine the paradox as a small lantern at the edge of a vast landscape. Its light does not reach far, but it glows steadily, reminding you that not everything needs to be seen clearly to be meaningful. Sometimes the soft boundaries of mystery hold more comfort than the sharp lines of certainty. Black holes, with their hidden interiors and vanishing horizons, remind us that reality contains layers we may not yet be ready to grasp. And that is not a flaw in our knowledge, but a natural part of exploration. Science often strives for answers, but meditation thrives in presence. The paradox sits at the intersection of both. It asks a sharp question: where does the information go? Yet offers no immediate solution. Instead, it guides us to reflect on the nature of answers themselves. Not every truth arrives quickly. Not every mystery must be resolved before we rest. Some simply accompany us, like a quiet companion walking beside us under starlight. As you breathe softly, allow the paradox to loosen its grip. Let it unfold not as a puzzle to be solved tonight, but as a rhythm, an ebb and flow of thought. The universe, after all, is not hurried. Stars take millions of years to shine. Black holes evaporate over unimaginable timescales. Even the expansion of space unfolds like a long, slow inhale. We too can slow down, allowing our understanding to grow gently rather than urgently. In this meditative frame, the information paradox becomes a metaphor. It mirrors the parts of ourselves we do not fully understand, our forgotten memories, our quiet fears, our unspoken desires, the mysteries of our own consciousness. Just as the universe holds truths behind horizons, we each hold experiences that cannot always be named or retrieved. Yet these hidden parts still shape who we are, quietly and continuously. Let this thought settle like a warm exhale. Not all mysteries are meant to be solved immediately. Some are meant to teach patience, soften the mind, and open the heart to the vastness of the unknown. And in their quiet presence, we discover a deeper kind of understanding, one that does not demand solutions, only attention. As our journey through the cosmos gently turns inward, the information paradox begins to echo something deeply human. We, too, have horizons, quiet boundaries where our understanding grows thin, where memories fade at the edges, where parts of ourselves drift into shadow. These horizons are not event horizons, yet the metaphor is soft and fitting. Just as black holes hide their interiors, we each carry places within us that remain unseen, even to ourselves. Imagine sitting at the edge of your own awareness, the way you might sit beside a calm lake at dusk. The surface reflects the world around you, but beneath it lies depth, stories, emotions, thoughts, and memories layered gently across time. Some are clear, some are forgotten, some linger like faint echoes, and yet all of them shape you, just as the unseen interior of a black hole shapes the gravity around it. We often believe that we should understand everything about ourselves, every feeling, every reaction, every choice. But just as the universe does not reveal the inside of a black hole, the human mind does not reveal all its depths at once. Parts of us remain behind quiet horizons, waiting for the right moment to surface. These hidden places are not failures of awareness. They are simply the space where growth and reflection take root. As you breathe softly, imagine your inner horizon expanding with each breath, not to reveal everything at once, but to offer gentle glimpses, a memory resurfacing, a feeling understood, a moment of clarity arriving like dawn light on water. You're not meant to know every detail of your inner universe instantly. Awareness, like cosmic understanding, unfolds slowly. The information paradox also reminds us that even when something feels lost, a memory, a connection, a piece of ourselves, it may not be truly gone. It may simply be transformed, reshaped by experience, woven into new patterns of thought and feeling. The universe's insistence that information is never destroyed becomes a comforting metaphor. Perhaps our own stories are never lost either. Perhaps they live on in the ways we grow, the choices we make, and the quiet strengths we carry. Black holes challenge the limits of physical understanding. Our own horizons challenge the limits of emotional and personal understanding, yet both invite the same gentle approach: patience, curiosity, compassion. The universe does not rush to reveal its mysteries. We do not need to rush to reveal ours. Let this idea rest with you like a soft whisper. Your inner horizons are not barriers. They are invitations to explore gently, to understand gradually, and to trust that what feels hidden today may illuminate your path tomorrow. As we drift further into the realm of reflection, black holes remind us of something profoundly simple, yet endlessly poetic. Light remembers. Even when stretched, bent, or delayed by gravity, light carries traces of every place it has been. Photons may take millions of years to reach us, but along the journey they collect subtle impressions, shifts in frequency, changes in direction, variations shaped by gravity and motion. In this way, light becomes a quiet recorder of the universe's history. Imagine a single photon leaving the surface of a distant star. It travels through open space, gliding past planets, dust clouds, and galaxies. Gravity tugs at it gently along the way, bending its path. Cosmic expansion stretches it into longer wavelengths. Every interaction, however small, becomes part of its memory. When that photon finally reaches your eye or a telescope, it brings with it the imprint of everything it has encountered: its colour, its energy, its timing. All whisper stories of its long cosmic journey. Now imagine light near a black hole. Its path becomes even more dramatic, looping, spiralling, stretching into red hues, lingering near the event horizon before escaping. These distortions are not obstacles, they are traces. They carry information about the curvature of space-time, the spin of the black hole, the structure of nearby matter. Even though the light cannot tell us what lies inside the horizon, it reveals a great deal about what happens at the edge. As you breathe softly, picture light as a gentle traveller, passing through the universe with patience, leaving no part of its journey unrecorded. Even when it seems lost into the black hole's pull, some of it escapes in arcs of brilliance, painting a glowing ring around the shadow. That ring is not merely light, it is memory made visible. This idea offers comfort. Even in the darkest places, information finds ways to endure. Light may disappear into a horizon, but the light that escapes carries echoes of what occurs near the boundary. And in Hawking radiation, faint, quiet, almost imperceptible, the universe seems to express yet another form of memory. Bit by bit, particles radiated outward might encode subtle information about the black hole's history, transforming darkness into whispering light. In our own lives, light serves as a metaphor for awareness. Moments of understanding, clarity, and connection act like photons, illuminating our path and carrying meaning from one experience to the next. Even when the path grows dark or uncertain, some light always returns, bringing with it the soft memory of where we have been. Let this reflection settle like a warm glow. Light may bend, it may fade, it may wander for ages, but it remembers, and in remembering, it keeps the universe connected. As we near the quiet crest of tonight's journey, a gentle realization unfolds. The cosmos remembers. Not always in ways we can see, not always in forms we can decode, but through patterns, correlations, and subtle imprints woven into space and time. Nothing that happens in the universe is ever entirely lost. Even when events fade from sight, when stars collapse, when matter falls into shadow, when light stretches into near silence, some trace remains carried forward in the deep structure of reality. Imagine the universe as a vast ocean. Each event, no matter how small, sends ripples across its surface. Some ripples fade quickly, others travel for billions of years, crossing galaxies, intersecting with planets, passing through dust and darkness. Yet no ripple is truly gone. Its influence becomes part of the water, part of the flow. In a similar way, every interaction in the cosmos contributes to the unfolding pattern of space-time. Black holes seem at first to contradict this gentle continuity. They swallow matter and light, hide their interiors behind a horizon, and eventually evaporate into featureless radiation. But the deeper we look, the more the universe whispers a different story. A story in which information transforms rather than disappears. Whether through holographic surfaces, quantum entanglement, soft hair, space-time foam, or subtle correlations in Hawking radiation, the cosmos appears determined to keep its history intact. As you breathe slowly and softly, imagine this cosmic memory as a quiet network of threads stretching through space. Some threads are bright, beams of light, gravitational waves, glowing gas. Others are invisible, quantum patterns, shifts in geometry, silent fields that encode the past. Together they form a tapestry that holds the universe's story, not as a rigid record, but as a living, evolving memory. This idea mirrors something deep within us. We too carry memories that persist even when details fade. Experiences transform. Emotions soften, perspectives shift, yet traces remain, shaping who we are. The cosmos, in its own way, seems to follow a similar pattern, remembering through transformation rather than preservation in its original form. Let this thought rest gently with you. Perhaps nothing is ever truly lost. Perhaps disappearance is only change. Perhaps the universe keeps everything in ways more subtle, more delicate, and more beautiful than we can yet imagine. In this view, the information paradox becomes less a threat to physics and more an invitation, a chance to understand the cosmos not as a machine that forgets, but as a vast, patient archive of everything that has ever been. As our journey through the paradox begins to soften, we arrive at a gentle boundary, the edge of knowing. This edge is not a wall or a limit, but a horizon of its own, a place where understanding fades into possibility, where knowledge blends quietly into wonder. Black holes sit at this edge, inviting us to lean forward, to listen, to sense the shape of truths not yet fully formed. Imagine yourself standing at this conceptual horizon, the way you might stand at the edge of a cliff overlooking a calm sea at night. The water stretches into a darkness that reflects the sky. You cannot see what lies beyond the faint glow of the moon, yet you know the ocean continues seamlessly. The boundary between what is visible and what is hidden is soft, shifting, almost tender. The edge of knowing feels the same. Beyond it lies not chaos, but simply more universe, more to learn, more to imagine, more to one day understand. The information paradox reminds us that science, for all its power, is still in conversation with mystery. It shows us where our theories shine brilliantly, in the structure of space-time, in the behaviour of quantum fields, and where they strain to meet one another. This tension is not a flaw, it is a guidepost, pointing us toward deeper principles waiting to be uncovered. As you breathe gently, consider that knowledge itself is never complete. Every new insight opens further questions, every explanation reveals deeper layers. In this way, our understanding expands like a universe in miniature, stretching outward, thinning at the edges, but never reaching a final boundary. The unknown is not an enemy of knowledge. It is the landscape in which knowledge grows. Black holes sit in that landscape as profound teachers. They show us that gravity can curve time, that quantum mechanics can tangle particles across light years, that information may be encoded in places we never thought to look. And yet, they also show us that we do not have the full picture. Something awaits us beyond the horizon, a principle, a unity, a deeper symmetry that will one day make the paradox feel obvious. But tonight, we do not chase that answer. We simply rest with the feeling of almost knowing, almost understanding, standing gently at the edge where clarity fades into wonder. This edge is where curiosity breathes. It is where ideas take form. It is where the universe invites us to continue exploring, slowly and patiently. Let this realization settle like the final flicker of twilight. The edge of knowing is not an end. It is a beginning, a horizon calling softly for us to dream beyond the limits of today. As our journey through black holes begins its gentle descent, we return to the question that started it all. Can information truly disappear? At the beginning of tonight's voyage, this question felt sharp, unsettling, almost paradoxical. Yet now, after drifting through horizons, entanglement, holograms, ripples, and quiet cosmic metaphors, the question feels softer, like a stone worn smooth by patient waves. In the earliest days of black hole physics, it seemed obvious that information was lost. Anything falling into a black hole vanished without a trace, swallowed by an event horizon that hid every detail. But then came quantum mechanics, whispering that information must be conserved, and then Hawking radiation, complicating the picture by letting black holes evaporate into seemingly random particles. Two pillars of physics stood face to face, each offering a truth the other could not ignore. As you breathe gently, imagine that original question floating once more before you, but now surrounded by deeper understanding. We have seen how information might hide on the horizon as holographic patterns, how entanglement might link the inside and outside of a black hole, how quantum hair and space-time foam might encode memories in delicate structures, and how radiation might carry subtle correlations that reveal the past bit by bit. None of these ideas is complete. None of them is final. But together, they suggest a single, reassuring possibility. Perhaps the universe does not forget. Returning to the first question does not mean demanding a final answer. Instead, it means appreciating how the question has changed, how it has stretched and softened as we explored the landscape around it. The paradox no longer feels like a contradiction, it feels like a guide, pointing toward the need for a deeper theory of space-time, one capable of unifying the smooth curves of gravity with the shimmering probabilities of quantum mechanics. This moment mirrors something within our own minds. Questions that once felt heavy often become lighter as we grow. Problems that seemed unsolvable begin to feel manageable. Confusion soften into curiosity. By revisiting our earliest uncertainties with gentler eyes, we find ourselves changed, even if the question itself remains the same. So we return now not to resolve the paradox, but to acknowledge its beauty, to appreciate how it reveals the subtlety of the cosmos, to recognize how much wonder can arise from a single puzzle whispered at the edge of gravity. Let this reflection settle like a quiet exhale. Sometimes answers do not close a question. Sometimes they open new worlds around it. As the night deepens and the pace of our journey slows, the information paradox begins to feel less like a problem to be solved and more like a quiet companion, a mystery that gently encourages us to dream beyond the boundaries of what we know. Not all mysteries weigh heavily on the mind, some lift it. Some open spaces where imagination can drift freely, unhurried and unafraid. The paradox of black holes is one of these, a puzzle that does not trap us, but expands us. Imagine lying beneath a sky filled with stars. Each one burns with the memory of millions of years, yet many are already gone, their light still crossing the void toward Earth. The cosmos is full of echoes, full of signals from ancient events happening long before our world even formed. In this setting, the information paradox becomes almost soothing, a reminder that there are still places where the universe keeps its secrets, where inquiry remains open, where discovery is not finished but ongoing. As you breathe gently, picture the paradox as a soft doorway rather than a barrier. It does not say, "You cannot know." Instead, it whispers, "There is more to learn." And in that whisper is a comfort, the assurance that we live in a universe vast enough to hold questions, mysteries, and unknown depths without demanding immediate resolution. Black holes themselves embody this quiet paradox. They are the simplest objects in the cosmos, defined by only a few parameters, yet they contain the deepest puzzles. They are both boundaries and beginnings, places where our understanding falters, yet where imagination flourishes. Their darkness is not empty, it is full of possibility. Their silence is not void, it is full of meaning. Allow yourself to drift into that feeling. Just as falling asleep involves letting go of the need to grasp every thought, exploring the cosmos sometimes means releasing the pressure to resolve every mystery. There is peace in the unknown, there is softness in uncertainty, and the information paradox invites us to rest in that space, trusting that knowledge will grow in its own time, like starlight travelling patiently across the sky. Let this reflection settle gently over you. Some mysteries are not barriers to understanding, they are invitations to dream. They help us imagine new physics, new insights, new ways of seeing the universe. They remind us that curiosity does not end at the horizon, it flows beyond it. In this quiet acceptance, the paradox loses its sharpness and becomes instead a lullaby, a soft melody that hums through the cosmos, encouraging wonder, reflection, and rest. As our journey approaches its gentle close, we turn now from the cosmos back toward ourselves, noticing how the vastness we've explored tonight quietly mirrors the world within. The information paradox, with all its subtle layers, reflects something deeply human. The way experiences shape us, the way memories linger, the way stories transform but never truly disappear. Just as the universe preserves its information in forms we do not yet fully understand, we too carry traces of everything we have lived. Imagine your life as a stream of moments, some bright, some shadowed, some forgotten, yet all flowing together to create the person you are now. Even when a memory fades, its influence remains woven into your thoughts, habits, emotions, and connections. The universe, in its grand symmetry, behaves in much the same way. Stars die, but their elements live on in new worlds. Light fades, but its journey shapes what we observe. Black holes swallow matter, yet the cosmos finds ways to preserve the patterns. Nothing is truly lost. Everything flows. As you breathe softly, feel how the cosmos is not separate from you. The atoms in your body were forged in stars older than Earth itself. The iron in your blood, the calcium in your bones, the carbon in your cells, all were shaped in ancient furnaces before being carried across space to become part of your story. You are, in a very real sense, the universe remembering its own past. And just as black holes challenge us to rethink the flow of information, your own inner experience invites reflection on how your past transforms into your present. The joys you've known, the challenges you've faced, the quiet moments of clarity. They move through you like ripples across space-time, not disappearing but evolving. Even the mysteries within you, the parts you don't fully understand, are part of this flow. They shape your gravity. They curve your path. They give depth to your story. Let yourself feel that connection now. You're not an observer standing apart from the universe. You are a continuation of it, a moment in its ongoing expression. The cosmos flows through you with every breath, every thought, every quiet wonder. In the same way that black holes may never lose the information they carry, neither do you lose the essence of your experiences. They soften, mature, transform, but they do not vanish. They become part of your internal horizon, shaping the person who moves gently through the world. Let this realization settle into stillness. The universe remembers, and through you, it remembers itself. You too are a keeper of cosmic memory, a story shaped by stars. As we reach the final stretch of tonight's journey, let your mind drift one last time toward the quiet heart of the paradox, not to solve it, but to rest within it. The information paradox began as a sharp question, a tension between what gravity predicts and what quantum mechanics insists upon. Yet as we've travelled through horizons and holograms, through entanglement and echoes, the paradox has softened into something calmer, something almost meditative. Imagine yourself floating at the edge of a black hole, far enough to remain safe, close enough to feel the gentle pull of its gravity shaping the space around you. The darkness is not threatening. It is peaceful, deep, and still. Around the horizon, light curves into smooth loops, forming a soft halo that flickers like the last embers of a cosmic fire. Time stretches, not uncomfortably, but in a way that encourages your thoughts to lengthen and dissolve, like waves smoothing themselves against the shore. Here, at this imagined boundary, the paradox becomes a lullaby. You feel the universe breathing, in the slow evaporation of black holes, in the patient unfolding of theories, in the delicate persistence of information woven through fields and particles. Nothing is rushed, nothing is lost. Everything flows into new forms, and as you breathe, you may sense that the boundary between the universe and yourself has thinned. The same laws that guide black holes guide your atoms. The same principles that protect cosmic memory protect the quiet continuity within your own life. Mystery is not something outside you. It is something you carry, something that moves gently through your dreams, your questions, your moments of stillness. Allow yourself now to settle into this final reflection. It is all right not to have all the answers. It is all right to rest in the unknown. The universe has spent billions of years evolving, learning, shaping itself. You too are allowed to take your time. Let the last threads of the paradox drift away like fading starlight. Let your breath slow, your thoughts soften, your awareness dim to a gentle glow. Tonight, you've travelled across horizons, through the folds of space-time, into the depths of gravity. And now you return to yourself carrying the quiet assurance that the cosmos is vast enough to hold both knowledge and mystery. And as sleep begins to rise around you, soft as a tide, let the final lines of AstraFlow settle over your mind like a blanket of stars. Everything flows. Sleep in that motion.